The next presentation is from Stellenbosch University. So please be prepared. The title is A Nano-Satellite Constellation for Tracking and Monitoring Endangered Wildlife in Developing Countries. So please.
Good morning, ladies and gentlemen. My name is Jan-Hielke, Roux, and with me here is my colleague Heunis, and we're going to tell you a bit more about our mission idea proposal, a nano-satellite constellation for the tracking and monitoring of endangered wildlife in developing countries. The International Union for the Conservation of Nature reports that 25% of the world's mammal species are known to be globally threatened or extinct. This is quite a shocking statistic that not a lot of people are aware of, and it's a clear indicator to us that there is a need for nature conservation activities around the world. And in that figure we have the Save Our Species conservation organizations project map, which maps all their current projects around the globe. And as you can see, they have quite a high concentration in the South American, African and Southeast Asian regions, and specifically around the equator. So our team thought we would investigate how we can apply satellite technologies to improve the efficiency of these conservation organizations. So we had some discussions with the Cape Leopard Trust and the Department of Conservation and Ecology at Stellenbosch University to help us identify how we can apply satellite technologies. So we identified two existing systems that they use for these conservation activities, and they include tracking collars and camera traps. Now, the animal tracking collars make use of GPS coordinates, and they store these coordinates, and the data is then retrieved from these collars. They are available in three different types. Firstly, you have a terrestrial collar, where a person has to physically enter the field of operation with a handheld antenna to retrieve the data from the collar. This involves a lot of time and manpower to retrieve the data. Then there's also GSM collars available, which makes use of cell phone networks to retrieve the data remotely from the collars. But these are rarely used, as the collars are deployed in remote locations where GSM signals are not available. And then finally, there is satellite collars, which makes use of services as Iridium to retrieve the data. But these are rarely used as they are very, very expensive. Not only the purchasing of the collars, but the data costs involved with making use of the satellite services. And then the other device is a camera trap, which is a motion-triggered camera device that is attached to a tree, for example, where it will take images of wildlife as it passes by. These devices are often deployed months at a time, where they will collect data. And the huge problem they have is there's currently no way to remotely monitor the condition of these devices. So it often happens that on the first day the device will fall from the tree or will be damaged by animals. So they lose months of potential images if the device is damaged. So we investigated how we can apply some nano-satellite technology to decrease the required amount of manpower and also provide affordable equipment to these organizations. So we set out a few mission objectives to provide affordable solution to developing countries, and we'll be doing this by deploying a constellation of nano-satellites to assist with the remote retrieval of the data from the devices. And as we are working with satellites, we have the opportunity to provide global coverage, but we want to place specific focus on the African, South American and Southeast Asian regions. And finally, we would like to automate existing ground stations to reduce some of the costs involved. So this is just a brief overview of our mission concept. We have the equipment in the field in the forms of tracking collars and camera traps. These devices will be equipped to be able to communicate with our nano-satellite constellation. The data will be uploaded to the constellation, where it will be transferred through satellite links to the closest available ground station. The ground station will then upload the data to a online web server where the data will be available to the end user from any location in the world. So this is just an animation of our ground coverage for the field equipment. Our constellation consists of 12 satellites in a pull string configuration at a 900 kilometer orbit in a 12 AM, 12 PM orbit. So the design of the constellation was primarily factored into the cost of the constellation as well as the coverage required. So from the end user perspective, we are providing access to new data twice a day with the 12 AM, 12 PM configuration, and our ultimate goal is to provide the service free of charge using forms of crowdfunding and donations. And something I also just like to point out is the choice of the 12 AM PM constellation is due to the activity of the animals. Since during the 12 AM period of the orbit, most of the nocturnal animals will be active, and during the 12 PM part of the orbit, most of the diurnal animals will be active. So it increases the likelihood of being able to retrieve the data from the collars. Our satellites will have three communication links: a UHF link for the field equipment, a S-band inter-satellite link, and finally a L-band ground link for towards the ground station. But if you struggle with finding L-band equipment for the ground link, as well as finding participating ground stations with L-band equipment, we can always shift that link to S-band frequencies if required. So with that constellation design, we can provide an access time of 105 minutes every 12 hours with a revisit time of 10.25 hours. And our estimates show that we should be able to service up to 519 devices in a specific area with a total throughput of 828 kilobytes. This is just an image of our inter-satellite link configuration. As you can see, we should not have any issues with interference from two further adjacent links, as the signal will have to pass through the Earth. In the event that we lose a satellite, the inter-satellite link will be broken, but it won't cripple the constellation, as the data can still be routed the long way around the constellation. And we also have the option to make use of our propulsion system to phase the satellites to close the inter-satellite link, as well as close the gap in the ground coverage. I'll now hand over to Heunis to take you further through the design.
Right, hello. So you've heard about the mission concept. Now onto the design of each of the satellites. For ADCS, we will, for sensors, just be using Earth sensors, sun sensors, and a 3-axis magnetometer. In terms of actuators, magnetic torquers, a Y-axis momentum wheel, and a propulsion system. The ADCS will have a number of modes. So on release, the satellite will enter a detumbling mode. We'll then place it into a Y-Thomson spin, and then use the momentum wheel to absorb the Y-axis angular rates. And then the nominal mode of the satellite is a stable nadir pointing attitude. So here's just a concept drawing of the satellite design. One point to note is that the thrusters of the propulsion system are in the Y-axis, although the satellite's velocity will be in the X-axis. This is so that we can take advantage of the momentum stored in the Y-axis wheel to counteract any disturbance torques when using the thruster. And we'll obviously need to precess the Y-axis to align with the satellite's velocity vector whenever we want to make use of the thrusters. So some of the other modes: orbit phasing, we'll need to phase the satellites to properly construct the constellation. So 12 satellites in the constellation, this will give us a 30-degree phase between satellites. And in the worst case, 180-degree phase shift will need to be made, taking 60 days and 48 grams of propellant. So we want to prevent the satellites falling more than 100 meters within their orbit. So we predict this will take about 12 orbit maintenance maneuvers over the 10-year period of the project, using 10 grams of propellant, and then finally at the end of the project lifetime we'll need to deorbit within the 25 years. So we'll first use the propulsion system to lower each of the satellites, where we'll deploy a drag enhancing device. Then the power design will make use of body-mounted solar panels on the plus and minus X facets, as well as on the negative Z facet. The figure just shows the instantaneous power generated over a single orbit. We'll be making use of 0.25 by 0.2 meter solar panels. Each of our satellites requires about 6 watts of power on average, and using this configuration we'll be able to generate 9 watts. So we have a safety margin there. We will be making use of passive thermal techniques to keep the temperatures acceptable. We'll be placing aluminium on each facet of the satellite that isn't covered with the solar panel. The estimated mass of the satellite is about 8 kilograms. And then, yes, we'll have a 0.25 by 0.2 by 0.25 meter satellite structure, which with the volume that we require, we could fit this into a 6U CubeSat structure, but then we would need to make use of deployable solar panels, and we would like to avoid this complexity. So at a 900 kilometer orbit, radiation can become a problem over the South Atlantic anomaly and the poles. So we'll be managing single event effects that occur with software techniques, as is the case in most small satellites. And then the total ionizing dose build-up can also become a problem over 10 years. And so we did a TRD prediction over the 10-year period using a 2 millimeter aluminum thickness, which resulted in a TRD of just under 11 kilorads. And this is quite manageable using commercial off-the-shelf components. So the implementation plan, we plan for a 18-month development time, after which we'll use a 3 phases to deploy the system. The first phase will consist of developing the satellites, constructing them, as well as testing field equipment using existing satellites. If this phase is successful, then we can move on to deploying a small constellation consisting of maybe 3 satellites as a proof of concept. After this, if this proves to be successful, then we can launch the entire system. So this is mainly done to just remove some of the risk involved with launch failures in operation. We plan for the total cost of the 10-year project to be 3.4 million euros. So in order to hopefully provide this service for free to developing countries, we plan to mainly make use of donations and crowdfunding to fund this project. So this has been shown to be feasible in the past with Kickstarter projects such as the ARCID Space Telescope program. Yes, so hopefully we can generate enough funding to make this project usable by developing countries. So just in conclusion, we hope that this project promotes and improves conservation activities on a global scale. Where we come from in South Africa, we have experienced firsthand the effects that habitat destruction and poaching can have on our natural wildlife. And we think that looking for ways to apply this type of technology to conservation efforts will pave the way for future advancement in conservation. Thank you.
Thank you very much for your presentation.
Yeah, thank you. The wildlife observation is pretty much dependent on how long you can observe the creatures and how often. And I guess if I understood it correctly, your constellation concept is providing 105 minutes observation time within 12.2 hours, so gap.
Yeah, in 12 hours. Every 12 hours there's there's that amount of connectivity.
Does this constellation comes out of a kind of requirement from authorities, or what? How did you choose that?
Okay, well, yes, so we had meetings with a couple of conservation organizations in the Western Cape, and we don't know exactly how often exactly they need the data or use it, but these aren't specific numbers. It's just numbers that we think it would be good for them to have this sort of data coming in regularly, and that's in terms of the collars, and then it's helpful for them to be able to verify that their devices are working correctly with that frequency.
So you basically thought the 12 satellites, that's it, and then these numbers come out of that?
Well, the 12 satellites was also chosen by balancing cost and coverage and antenna beam width that we could achieve, and so there were a lot of small factors.
Your thrust amount in the y direction, how do you intend to precess your spin vector of your momentum wheel to align it to the velocity to maintain the constellation or to deorbit at the end? What type of actuators do you plan using for that?
Well, I imagine we'd be using the Torque rods, and we would be doing this over 2 orbits to prevent generating a high gyroscopic disturbance.
So have you simulated that to make sure it will work?
Yes, I haven't personally simulated, but it was simulated.
So as for the total system cost, including the ground equipment, namely in this case, the tracking collars and the monitoring system will be the most cost factor within the whole system. So with this, do you think how much you can reduce the cost for monitoring systems on the ground? Because that seems to be the most important factor in terms of the cost.
Yes. Okay. So so that cost that I had on the slide there does not include the field equipment. One thing that we do hope to achieve with this, there has been research done at Stellenbosch University to construct cheaper versions of these, well, specifically the collars, because the current collars provided by other services that make use of satellites are really expensive and not very affordable for organizations that we spoke to. I'm not sure if we have a specific cost for the field equipment that we can provide, but it is significantly cheaper than the current options.
That would be the most effective aspect of this project, I presume.
What, the decrease in the cost? Well, that
system
is the main advantage that we will provide with this system over existing ones.
Right.
Yeah.
So I'm interested in the user equipment. So you put some sensors or some transmitter on the body of some wild animals, and how long does it survive? Because it's a battery program.
Yeah.
And so in order to reduce the battery, it's better to know when the satellite is coming. And so how do you think about that? So you have some special treatment about that?
So I don't think there were any plans to predict when satellites will be passing over, but I think at the moment, I know with the camera traps, they need to replace the batteries about every 2 months, something like that. So I assume since collars aren't capturing images, it's quite a lot longer than that. So that's about all we thought of in terms of
every 2 months. You should
camera
replace.
traps, yeah.
Okay.
So yeah.
So that length is enough to monitor the wildlife, ecology.
Yeah, well, it captures images within those 2 months, and then, so yeah, what our service will do is then ensure that it's working correctly in the case of the camera traps, that it's, hasn't just been sitting there for 2 months.
Okay.
Yeah,
good.
and they haven't wasted that time.
Okay.
I'm on a debris rampage today because you also put your satellites at 800 or 900 kilometers, and that upsets me. But in addition to that, the reason that I wanted to point out is that you're putting them high and you're saying, I'm going to use the propulsion to bring them down after 10 years. Now, 10 years for COT component is an optimistic value. And my concern is if you have a failure, then the propulsion system is not available. So you're creating debris. And my concern is the first time one of your satellites fails before the orbiting, they're going to ask you to deorbit the rest of them from a debris perspective. So do you guys have any plan, or have you thought about how would you solve that?
So the deorbiting if the propulsion system is not available?
No, if you have an electronics failure because over the 10 years, something goes wrong, then you cannot deorbit the spacecraft anymore because the propulsion is not going to work. You cannot command it. The radio breaks.
Okay.
You're stuck. Have you thought about that?
No, well, okay, maybe my colleague has the answer, but if I were to try and think of a solution right now, I would just, you could maybe program it to deorbit automatically after 10 years.
Yeah, fail-safe.
Yeah, like a fail-safe.
Okay, thank you very much.